This is a production of Cornell University.
What I'd like to talk to you guys today about with the nitrogen cycle is actually what are the controlling factors. Okay, so what's controlling these things, and to a certain extent, what is the consequence of this, of what's controlling these factors. So it's about nutrient cycling, the issue of essential for life and its availability, that thereof sort of controls this distribution. And this availability is controlled by these three things, these issues of the two different types of sources, the sinks and the pools, and I don't know why there's not sinks on that slide, and then the fluxes. Okay? Now these nutrients it's sort of each to its own because you need to have a very specific type of, the nutrient has to be in a very specific form for these organisms to use. Okay? Now, the largest sink of these nutrients are generally unavailable. Because of this each to its own, the largest pool of these nutrients are generally unavailable to organisms. Okay? And so what you're looking at is a progression of different processes that produce a form that the organisms can in fact use. Now, there's a large amount of specialized organisms that in fact transform this unavailable pool into a usable form and thus make it available for all the other organisms. Okay? Much of this transformation of these nutrients, I mean, this is a soils course, so I want to talk about what the factors are in soils that are in fact controlling this. Okay? So much of this transformation of nutrients is in fact controlled by those soil characteristics, which are then controlling the organisms that are doing the transformations. Does that make sense? Yeah? Okay. So, back to these questions. These questions are basically building, okay, what are the pools, what are the sources and losses, and what are the fluxes? So we've basically answered these. Okay? Now I want to have an understanding of what's controlling these fluxes. Okay? And that brings us back to this slide. Okay? In the soil environment, what is actually controlling the nitrogen? All right? Now to answer that question, I want to basically pull things apart for a little bit. And I want to talk about what those sources are, what those sinks are, and what the specific fluxes are. That's what they are right here. Okay, let's list them. Okay, things that are going into this system. There's primarily three types. One is anthropogenic, human source material. Okay, this could be intentional or unintentional. Atmospheric deposition is a big one. You know, those stacks are emitting stuff, and those stacks are blowing downwind and mixing with the water, and basically it's coming down. Okay? We also have inorganic fertilizer as well as organic fertilizer. And then we have all these waste products. We're fertilizing the world, in essence. The sinks, where is the nitrogen? Well, the largest pool is the atmosphere. Then we have the biosphere, the biomass, and then finally we have the soil. The largest pool by far is this atmospheric pool. Okay, now these are the sources, there's the pools. What's controlling this flux between these pools? Basically, we're looking at a mobilization, and if we go back to the nitrogen cycle, that is that mineral versus a mineralization, a mobilization, mineralization, that's an ammonification through nitrification. That's the mineralization component. Okay? We have denitrification, taking it from the end of nitrification and turning it into N2 gas. Okay? Do we then have fixation, where it's taking that N2 gas, and it's biologically as well as abiotic, but it's basically taking that N2 gas and putting it in an ammonium form. We then have plant uptake, taking that ammonium form, as well as potentially taking it in the nitrification form. And then finally, the nitrification form and the ammonia form, basically we potentially have losses through leaching as well as through volatilization. Okay, so those are the fluxes. These are the pools, these are the sources. Do we feel comfortable with that? We talked about this. And there's the cycle. Does the cycle make sense? The interesting thing about this, and we're going to be talking about three other nutrient cycles, and one of them I really shouldn't even be calling a cycle. The interesting thing about this nutrient cycle is that it is entirely mediated. It can be, I should say, it can be entirely mediated by biological organisms, primarily microorganisms. every one of these steps that you see here, the fluxes are controlled by microorganisms. The microorganisms are then controlled by environmental factors. And this is a soil-driven system, except for the nitrogen fixation, which means it's soil conditions that are controlling these fluxes. So here are the fluxes again: immobilization, mineralization, nitrification, fixation, plant uptake, leaching, and volatilization. So what is going on in the soil that controls these fluxes? Now, you're going to see this question for each one of the 4 nutrients that we're going to be talking about. And it's going to be basically the same thing every time. It's going to be temperature, moisture, climate, oxygen, and then the element itself, i.e., in this case, nitrogen, but more importantly, the form of that nitrogen. So let's start with temperature. This is a simple slide. You guys have seen this, I'm sure, many, many, many times. Okay? Biological activity versus some sort of gradient of temperature, degrees Celsius. Okay? There's a cold point and a hot point, and someplace in the middle you have maximum biological activity. Okay? When you start getting too hot, the system starts slowing down because you're starting to see denaturing of proteins and things like that. When the system gets too cold, the organisms can't operate because the biological activity at 0 is basically 0. That was not meant to be funny, but I don't think anybody thought it was funny, but it was funny to me. All right. Makes sense? Okay. Now, when we start thinking about moisture, I should actually put this at the back. This should be my last slide when I talk about moisture, but I like talking about this first because this really brings human activity into this sort of nitrogen cycle. Okay. What you see here is sort of a rice paddy or a wetland. Okay? And one can imagine in a wetland or rice paddies, we're basically looking at water as a dominant feature of that landscape. Okay? And let's talk about the nitrogen cycle, because rice, and as well as all these other plants, they need to have nitrogen in their plants. I mean, that's part of their essential nutrients as well. So let's use a rice paddy as an example for how we, in fact, control nitrogen cycling. Okay, so I've got a water level here. Okay, here's my rice plant. I have an aerobic zone of soil here. There's enough exchange between atmosphere getting oxygen into this water that it can get into this zone. Okay, if I get down below here, I'm in the anaerobic zone. Okay, now keep in mind that nitrogen cycle and what's controlling things. Now, if I am a rice farmer and I need to get nitrogen to my plants, what potentially should I do? Because I have an aerobic zone here, I could put in a surface applied urea. Okay? Now this urea is basically an ammonium form, in essence. Okay? And this material potentially will volatilize from the system because it's in a ammonium form, basically. Okay? And my nutrients potentially won't get to my plant. Potentially. Now, I also potentially can have that urea, the ammonium, basically go through nitrification. Now, this system is aerobic, so I can, in fact, have nitrification. Make sense? This nitrate is soluble, so I potentially will have downward diffusion or fusion movement out of the system. Okay, through leaching, and I can have loss. Now, the interesting thing about denitrification is denitrification through nitrification is an anaerobic process. I will not have denitrification in an aerobic zone. Does that make sense? So, if I add my nitrate here, I'm not going to lose it as nitrate into gas. It's not going to be going that way because I have oxygen here. But the minute this nitrate gets down into the soil, which is anaerobic, this nitrate can now go through denitrification and turn into N2 gas, an unavailable form for plants, and it volatilizes and is lost from the system. Now, as a farmer, I know that nitrification is controlled by oxygen. Now, theoretically, if I put this ammonia here, I can lose it. But what happens if I take this ammonium and I put it into the anaerobic zone? If I put it into the anaerobic zone, I will not get nitrification because it has to be in an oxygen presence. The microorganisms that mediate this, the Nitrosomonas and Nitrobacter, need to have oxygen. So if I put this ammonium in the anaerobic zone, I shortchange this, I stop this. And if I stop this, I'll never get this, so I won't get the leaching. Make sense? Now, the truth is this stuff can diffuse upward as ammonium. It's a gas. But it also can diffuse into my rooting zone. So as a rice farmer, if I had ammonium as my fertilizer, it makes sense for me to put that into the anaerobic zone because I'm going to maximize the uptake of my plants and reduce the amount of nitrification. Does that make sense? Now, as a farmer, does it make sense for me to put nitrate down here as a fertilizer? Certainly it's going to be soluble, it will move with the water. But also, because the system is anaerobic, I'm going to be encouraging denitrification. And if I encourage denitrification, these are forms that the plant can't use, and it's a gas, so it will escape my system. So just by knowing the nitrogen cycle and what's controlling those fluxes, I have an idea about what type of fertilizer I should use and where I should put it. Good application of the nitrogen cycle. Questions? No? Cool? All right. Now let's step back a little bit and not be so sort of management based, but let's actually think about sort of the management that we do just by our daily lives. Okay? This is two different landscapes here. We're looking at an urban landscape or a developed landscape versus a forested or undeveloped landscape. And what we're basically looking at is we're looking at soil drainage classes. As you move through this profile from the uplands down towards the stream that's sitting here, you're going from well-drained soils up the uplands to somewhat poorly to very poorly drained. Okay, so we're basically looking at a topo sequence in this case of an upland system, of a developed upland system, a topo sequence from an upland system in the forested going down into the stream. Okay, the assumption is the water is moving this direction. Okay, now the size of the bars basically measure the height. The higher the bar, the more denitrification you have. Okay, what's denitrification? We're basically taking it from the nitrate to N2 gas. All right? What's controlling that? Go right back here. Denitrification is being controlled by this anaerobic system. You won't get it up here in the aerobic system. You only get it in the anaerobic system. Okay, so we look at the urban event versus the rural. In all cases, no matter where you are in the system, in all cases, denitrification is higher in these urban environments versus these non-urban environments. Now, why? The reality has to do with how we manage our water. It's not that there is potentially more nitrates here than here. I mean, we fertilize here. We don't necessarily fertilize forests, at least intentionally. Okay, yes, we have acid rain and all that. Okay, but in an urban environment, there might in fact be more nitrogen. But we're talking about denitrification, the rates of denitrification. What's controlling it?
Are you picturing agricultural areas as developed?
Well, agricultural areas could be developed, but I think we're also thinking about all the infrastructure that's associated with this. Okay, what happens when it rains in an urban environment? Things get wet. But where does the water go? As quickly as possible, they try to concentrate it and move it off. Okay? They put it into large water systems, and basically they saturate the systems. The systems go anaerobic, right? In essence. Ish? Make sense? Okay? So if I'm trying to capture all of this and put it right into these zones, okay, I'm saturating down here. I'm flooding this zone while I'm trying to dry this zone out. Okay? This zone is wetter than that zone up here, but the whole system Yeah, the whole system is somewhat wetter, but it's not all concentrated. Okay, it's not all saturated. It's wet, but it's not saturated. Okay, so if I'm delivering more nutrients and I'm making the system more wet and anaerobic at the same time, not just wet, but wet and anaerobic because I'm concentrating it, what do you think is going to happen to my nitrification rates, denitrification rates? They go up. And so as a result, we see these quick responses of denitrification. Does that make sense? Now, this is not intentional management. Well, it is intentional management, but we're not intentionally managing nitrogen. We're intentionally managing water. And if the nitrate is moving in the water and we concentrate it, it goes anaerobic really quickly because we have these large storm sewers versus over here where we don't have that kind of concentration. The system's going to go anaerobic. We're delivering more nitrate. We're going to have higher levels of denitrification. Make sense?
This has been a production of Cornell University, on the web at cornell.edu.